All right, we will cap off topic 5 by introducing you how to use the Z tables. Probably you probably know how to use these Z tables as well. So, as an addition in the end, if you have correct or if you have certain models of calculators, I'll be teaching you something to elevate how you would normally solve these kinds of problems. Okay? So hopefully you have, I don't know, in this case I have an FX 570 ES plus. So I think FX happening. Oh, hold on. Okay, there it is. I have an FX 570 ES plus currently with me. I also know that class whizzes can do this ES and then EX both work. Canons as well, a Canon F789 SGA, basta the more recent ones. So I recommend you play around with your calculator right now. Just see if you have a stat mode. If you have a stat mode, most probably you will have or you will contain, or rather your calculator contains the shortcut or the technique that I'm going to teach you. But that is my hook for now. Right? So what they say in here in pages 735 and 736, we have our Z tables, which contain the cumulative probabilities of a normal probability distribution function. Right? What we will see in here is that, well, we will see values that roughly go up. Roughly go up. This is 0.0003. And they will go up, 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 up until, well, you get to a point where it is 0.5. What does that mean? Well, again, what we're seeing in here are cumulative probabilities. Note that what happens, or rather, how this do you call this? How this table works is that you will have in here your ones place and your tenths place, and then in here you will have your hundredths place. So in this case, what we say for example, mean when we have 0.0052 is that it aligns with negative 2.5 and then there's a 0.06. What this means is that 0.0052 is the value for negative 2.56. Okay, so that those are your areas under the normal curve. What this means basically is if we catch that same thing, negative 2.56, if we now go to my Desmos in here and we try and account for that value, and here is negative infinity. And then here we have negative 2.56. What we will see in here is that this area right here has this region right here is an area of 0.005233608, so on and so forth. That is the same value as in here, 0.0052. So again, a lot of your stat tests will be super mega easy if only you had graphing calculators. But most probably you don't have graphing calculators with you. So, well, you're going to have to make do with Z tables, right? So they're going to see in here, they're going to explain in here basically the same thing that I've explained to you, right? The first row, the next decimal, the first column shows the Z scores up to one decimal place, and then the first row in here, the column headings are the next decimal, are the hundredths place. Yeah, the hundredths place. Right? The values in the cells are the cumulative probabilities. If you are confused or you've forgotten, hopefully, this very helpful drawing on top in here will help you remember that that is what's supposed to happen. This is your value of Z. This is your value of Z. Right? And notice that these are all negative values. So they're going to be somewhere in here. And as a result, they're going to be tiny. And this is tiny. Okay? So that's what's supposed to happen. Therefore, notice that if you're going to go back in here and you're going to look at the second table, right? Notice these are now positive values, and of course, they're going to be humongous. Why? Because, say, for example, at 1.00, it'll be 0.8413. Because if you go all the way to 1, that's a lot of area. It's 0.841345. That is how you're supposed to think about it. Okay? The values in the cells are the cumulative probabilities. For example, what they see in here, or rather, what they've provided in here is the probability that your standard normal, that your z-score is negative 3.21 or lower is 0.0007. If we put this in Desmos, negative 3.21, of course, Desmos will agree it is 0.00066, which means 0.0007. Okay? I suppose one of the weaknesses of the lower and the higher values is that, well, there's a lot of 0.4s, there's a lot of 0.3s, oh, sorry, 0.0004s, 0.0003s, so on, so on, so forth, right? But I suppose that is only because, well, these are very small areas we are dealing with. And what they have in here as well, if your value is less than, or rather, if your z-score is less than negative 2.76, of course, negative 2.7, and then 0.06, you'll have, what is this? 0.29%. Okay? And then they have more. Okay? So in this case, what they're going to ask us now, what is the value of your probability? What is the probability that your z-score is less than 0.52? Well, 0.5, and then 0.002. Oh, there you go. 0.6985. Z is less than or equal to 1.44, 1.4, 0.04. Oh, that's 0.9251. And then 2.97. Well, we don't have the 2.97s in here. That is too far up, right? So we're going to have, oh, sorry. So I suppose we should just look in our own tables in here. 2.97. So the sevens are all here. 2.97 is therefore not 0.9985%. Oh, sorry, 0.9985 or 99.85%. Because of course, that's going to be quite high. Look at this. Positive 2.97 gives you 0.998511 area. This is an area. Okay. And then, how about the value that your z is greater than 1.16. Now notice, wait a second, this is different now. Why is it different? Because if we're not thinking about a z-score that is bigger than 1.16, say for example, this is your bell curve, for all of this time, say for example, this was 1.16. For all of this time, we've just been shading the left-hand side because it's less than or equal to or less than a particular number. But because of this bigger than, we are now shading the opposite region. How are we supposed to get the opposite region? It seems that there is no value, but there is. Note that the total area of all of the curve is 1. And you know the area of this thing that I will lightly shade right here. The area for there is 0.8770. Therefore, this area right here is just 1 minus 0.8770 or 0.1230. That is now your value of z is bigger than 1.16. And at this rate, right, I am now expecting you guys to be able to be somewhat proficient in navigating these changes, right? We will have more drills about this, but suffice to say, that is how you're supposed to get it in the beginning. There you go, right? We have invoked the law of inverses, 0.1230. Next, what if it's a range? What if it's no longer a cumulative distribution? What if it's between 0.47 and 1.08? How are we supposed to get that value? Now let 0.47 and then 1.08. Suppose we should just do negative 3.5, positive 3.5. The step is Then this same. This is the same. Point zero. Okay, there you go. We are being asked what this sliver of area is. And you might think, wait a second, I think I've seen this before, especially in the exponential distribution. In the exponential distribution, if we are being asked this sliver of area, it would be nice if we knew the red and the yellow areas. And we do. The same way that if we're being asked for this area right here, right? We're being asked for this area right here. What will happen is that, well, you might need to have this area first, and you might need to have this area as well. Because if you subtract them, you will get the difference, which is this sliver of area, which means you're going to have to get two different values. In this case, 0.47 is 0.6808. 1.08 has 0.8599. You will get their difference. 8599 minus 0.6808 1917 is 0.1791. There you go. That's how you're supposed to put it all together. Okay? So now we are being asked many other values. So the z value, or rather, what is the probability that your z value is bigger than negative 2.81? How will that work? Right? How will that work? Well, in this case, you just need to get your value of negative 2.81, which is 0.0025. But that is not, that is not your value because it only talks about this area right here. What we're talking about is a z-score bigger than negative 2.81, aka the remaining area right here. And in that case, of course, that is just 1 minus 0.0025, which is 0.9975. And in this case, of course, Desmos will agree. Negative 2.81. And then if we set this to infinity, it will agree, 0.997523. There you go. Okay. Now, from negative 1.96 all the way to 1.96, what is the probability of that z-score being in that region? Well, you might say to yourself, well, I only have the negative in here. What about the positive? You actually can only, you can actually get the answer in here if you just know negative 1.96. Oh, you don't know pala. Never mind. Okay. Let's go to negative 1.96. You might think to yourself, oh, I need to get the value for negative 1.96. So negative 1.90123456. You need to get the value of negative 1.96 and the value of positive 1.96. But I will tell you right now, you don't have to go up to here, right? Why is that? Because, well, oh, there you go. This is all you need, honestly, right? So this value right here is 0.0250. What do we mean? The probability that, 1.96 and then z, then 1.96. The only thing that you need to know is that f of negative 1.96 is 0.0250. What am I talking about? Right? We have this. Ooh, that is very bad. Okay, that is worse. Okay, we'll take it. Right? We have negative 1.96 in here, and we have positive 1.96 in here. Basically, what is only being told here to us is that this area right here is 0.025. How am I able to get what this value is? Well, give it a little think, right? Pause the video if you would like, and confirm the answers with me once you're done. But the thing is, I know, number one, that this area right here is 0.0250. Number two, I know that this graph is symmetric. Therefore, I know that this value is also 0.0250. If we're being asked what the area is in the middle, I can just know. Number three, the total area of this is 1. Therefore, my answer would be 1 minus 0.0250 minus 0.0250. We will get a square 95%. A 95%. Okay. And now, that is where it ends, I suppose, for the normal examples. This is now where I ask you all, or rather, where I teach you all how to do it in the calculator, right? And what I mean, or sorry, before I teach you all how to do this in the calculator, everyone's calculator is different, right? Please look at your calculator manuals first. If for some reason, right, you've already been playing with your calculator, you don't see a stat mode, I'm so sorry. This cannot apply to you. Right? You might want to borrow a newer calculator perhaps. Right? But in this case, given a standard normal distribution, find the area under the curve that lies blah 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 blah. We don't need to look at the table. I will now ask you, or rather, I will now teach you how to, well, get the values of these without even looking at the table. Okay? Don't tell your other fun stat profs, I suppose. But in this case, right, what I want to do first is I want to share with you the calculator manual for the FX570ES Plus. What they have in here are values that are called, or rather, are functions that are called P, Q, and R. P, Q, and R, notice what exactly is happening. In this case, we have performing normal distribution calculations. Okay? This is exactly what we need. Look at that. P of T is identical to whatever it is that you can find in the Z tables. Right? Q starts from 0, starts from your mean, and goes up until the value that you have selected. R, on the other hand, goes the other way around. If you notice, P and R, right, are opposites of each other. Right? So in this case, what you're supposed to do is this. Say, for example, you want to get the area under the curve to the right of Z is equal to 1.84. So again, you have this bell curve right here. You have 1.84 in here. You want to get this value of the area. What you might do if you had the Z tables were, what you might do could be something like 1 minus f of 1.84. That is totally valid. Okay, I get that. But you are very lazy, like me. So what do you do in this case? Well, number one, find the stat mode for your calculator. In this case, for mode, for the Casio 570ES Plus, it will be mode, right? Mode, the one on the top right, just very close to the on button. If you now press mode, you'll now be presented with many different modes that the calculator can do, I guess. And then what you will have is usually number 3. Number 3 is reserved for stat or statistics. If you press number 3, you'll be presented with even more options, right? So in those cases, you will have basically different regressions. If you don't want to go into that rabbit hole, you don't have to, right? That is for your data engpa. But for now, let's just select the easiest one. Number 1, one variable. You will now be presented with a table like this. 1, 2, 3. You have your X, and then this is currently highlighted in here. What you will do is immediately press AC. Right? AC, or in this case, CA when you're using a Canon. I remember that. And now, it all depends on how your calculator is programmed. For many Casios, what you will do is shift, right? Shift, notice that is the top leftmost button. It is the one that is colored yellow or gold, right? And what you will notice is that there is a color gold, or sorry, that there is a word stat colored the same way as shift at number 1, right? Something here. If you press shift 1, what will happen is that it will open options for functions or something else about this mode. This mode has, well, normal distribution calculations. So notice that in number 5, In number 5, what you will see is the phrase DISTR. Of course, distribution. Right? And then after that, you will be able to see that for if you choose number 1, what you will be given is P. For number 2, what you will be given is a Q. For number 3, what you will be, oh my gosh, this is where my face is. I'm so sorry. I should put this here. For 1, you'll be given the P. For number 2, you'll be given the Q. For number 3, you'll be given the R. And then for number 4, you'll be given this thing, D. We're not going to go into number 4. We are just using 1, 2, and 3. Okay? Again, for the people who have other calculators, please refer to your calculator manual how you're supposed to be able to get this kind of these kinds of commands, right? For more recent values, or sorry, for more recent models of either Casio or Canon calculators, they have an apps for the Canon, and they have, I think, option for ClassWiz, right? So if you don't have those options, of course, just again refer to your calculator manual for instructions. Okay? What we will be using is, of course, numbers 1, 2, and 3. Kayo na bahala how you want to solve this one. Okay? But for me, I can very clearly see that out of P, Q, and R, the one that would make my life the easiest is the R function. The R function, basically, if you're going to press Shift 1, 5, and then 3, what will come out of your screen is this letter R. And then to the right of what? To the right of 1.84. And of course, you close that with parenthesis. And then, therefore, you'll be presented with the immediate final answer. And not only with the immediate final answer, but also a final answer to 6 decimal places. Right? 0.032884. On the other hand, if we have done the same thing that we have done earlier about using the Z tables, if for example, you have 1.84 right here, 1.80123.4, 0.9671, right? 0.9671, 1 minus 0.9671, you will get 0.0329. That is your value. You can see that they're the same, but this is even more accurate. Very interesting. Okay. Excuse me. Right? So that's how you're supposed to do it. Okay. Letter B, between z is equal to negative 1.97 and z is equal to 0.86. We'll have this negative 1.97 is here, and then 0.86 is somewhere in here. What we want is this area right here. Now, right, what you would do in, what you would do in cumulative in the Z tables would be to get the cumulative probability at 0.86 and then subtract that to the cumulative value of the Z table at negative 1.97. That is the way to do it. But in here, we actually have, we have many different ways for you to do it. Number 1, if you think about this shape right here, what I can see is that number 1, this is really just this minus this. Right? Basically, what we're doing is the same thing in here. What do I mean? Why do I need to say that out loud? It's because, well, you have in here the function P of T, which is the cumulative distribution. What I can enter in my calculator is P of 0.86 minus P of negative 1.97. What I can also think about this bell curve as is, say, for example, something like this, right? That is just equal to this plus this value right here. What am I talking about? It's this left-hand side and this right-hand side right here. What are you talking about? Well, if you notice, the Q function starts from 0 and ends until your argument, until the thing inside the thing inside of the function. So in this case, this corresponds to q of 0.86. That is going to be this area right here from 0 to 0.86, and you add it to, well, negative 1.97. This value from 0 all the way to negative 1.97. Okay. Well, I suppose the last one, if you really want to, I'd say, for example, you have something like this. You can get the area by getting the full area minus getting this right-hand area and then getting this left-hand area. Or in other words, 1 minus, right? This is P of negative 1.97. Then minus, this is R of 0.86. I don't know who would do this, but hopefully you guys are getting the idea of how to use these three functions in accordance with one another. Okay, so let's just pick one right here. Something like, I don't know, let's use Q so that we're very cool, right? I don't even need to get the value of these things separately. I can just add them all together. Shift 152. Q of 0.86 plus shift 152. Q of negative 1.97. We will get a value of 0.780690. That is your more accurate kind of computation. If we instead use this, we would get 0.86. Let's use 0.86. 0.810123456 0.8051, and then minus negative 1.97, negative 1.90123456 0.0244. Oops, 0.0244, 8051. Sorry, 0244 is 7. This is 0. This is 2. This is 8. Oh, sorry, 0 minus 2. Sorry, that is sorry, 7807. 0.7807. Yikes. Sorry, the mental math was not mathing. You can see that they are still, well, the same, but if you do not want to look at your tables because you get dizzy, like me, you can use your calculator for this one. Okay? I will not be disallowing this in my exam. I think, or rather, I hope you guys use this because, well, it's really handy. Okay? It's really handy. Now, what about other things? Right? What about more dubious kinds of questions like this one? So what should K be if Z less than K is 0.6915? What? What does that mean? Right? What should K be if Z less than this score is 0.6915? Well, we are asking now a reverse of the question. Say, for example, we have this bell curve right here, and we start shading from the left all the way to the right, and then we stop at a particular value. And then we stop it, we say, oh, wait a second, this area that I've shaded is 0.6915. What is this value that I stopped at? That value, of course, would have to be reverse engineered from the Z tables. Sadly, there is no thing that will help you through this based on your calculator. You really are going to have to reverse this based on what do you call this? Based on the Z tables. So in this case, you're going to have to find a value whose cumulative probability is 0.6915, which is apparently 0.5. That is your K. Okay. Next, what should K be if Z greater than K is 0.3264? Notice that we are in the wrong table, because 0.3264, all of the values here are bigger than 0.5. But we're not. We're in the correct table. Why is that? Because now look at this. This is greater than. Oops, sorry. This is now greater than. So in this case now, they were shading from the right. So if they shade from the right, what value k would this be if the area in here were 0.3264? Or in other words, if we were to invoke the law of inverses, this area right here should be equal to 0.6736. 6736. Let's just find where that is. And there it is. 0.45. Okay, 0.45. There you go. And there it is. Okay, what should k be if if the probability of the z-score being between negative 0.93 and this value k is 0.7235? You might think now, wait a second. They're now using a range. Oh, we should go for the negative 0.93, excuse me, first. Excuse me. And in this case, actually, we don't need to go to the negative values because we already have a value of 0.93 in here. You might say to yourself, wait a second, why? Well, it's because something like this. Oh, sorry. I suppose we can go here. Okay. Oh, oh, oh. Okay, there you go. We want a value of negative 0.93 up until this value k, such that the area is 0.7235. Therefore, this area right here should be 0.7235. How is that going to happen? And how is that going to happen even without us knowing the value of negative 0.93? It's because we have already a value of 0.93 in here, which is 0.8238. You're going to say, wait a second, how would I know what the values are of there? Well, if you think about this, right? Oops, sorry. We know that this value of 0.93, let me have negative 0.93 in here as a reference. We know that this value right here, oops, we know that this value right here has an area of 0.8238. So therefore, via the law of inverses, we know that this area that's remaining is 0.1762. Okay, that's the one. But this is not what we're looking for. Number two, they're symmetric. If you flip it like that, you know, oh, this one is now 0.1762. And we want our value to be 0.7235. So that means if this value right here were 0.7235, if we add these two values together, that means that our cumulative, right? That our cumulative should be 0.1762 plus 0.7235. We will have 7998. 0.8997 should be our total. So in this case, 0.8997 is exactly here. There is your k value. Your k is equal to 1.28. There you go, 1.28. Okay, and so in here, we can do the same thing, right? 0.3015. Well, this is greater than. Huh? So we're going to do this, right? You guys will find that I use visual aids very often. It's because I just want to think about the areas. Z greater than K is 0.3015. I know it's somewhere in here because it did not pass 0.5. If it passed 0.5, then that means it would have been a negative value. And honestly, we can just look at the values from earlier, but we need to first invoke the law of inverses. 1 minus 0.3015 should be 0.6985. 0.6985, that means 6985. There it is. That is 0.52. There you go. k equals 0.52. Next, here, right? We will now have this this value of k is less than 0.18. 0.18 is over here. And, well, this value of k needs to be somewhere in here for this area to be 0.4197. And just like earlier, we can think about this as, wait a second, I know, or rather, I'm supposed to know what the value of this shape is. This boot right here, this boot right here. If I minus that, if I take the difference of that with this little area that I'm shading right now and here, we will get our value, which is supposed to be 0.4197. Let's look at our value of negative 0.18 in here. Where is that? Oh, I can get it from here. 0.18, so 0.5714. You might say, what are you doing? Right? In this case, we know that this is 0.18, this is negative 0.18. Right? This value right here, this total right here is, I forgot, 0.5714. 0.5714. And in this case, by the law of inverses, this should be 0.4286. 0.4286. But again, if we flip it like this, we are going to know that, oh, I see that this is going to be 0.4286 as well. And so we just have to find out what this value is. 0.4286 minus x is equal to 0.4197. If we took those two things, 4197, we will get 9, 7. Okay, 0.0079. Is that right? Let me just get my calculator. 4286, 4197. Yeah. Oh! Sorry. Oh, nga po, 0.0089. Sorry, that is my bad. That means that this value in here needs to be 0.0089. But I'm very lazy. I think I can do it in here. Never mind, I can't. These are too small. These values are too small. So I just need to get, right, my tables up until the point where I see 0.0089. 0.0089 is here. There you go. That is now negative 2.37. Negative 2.3. Okay. Negative 2.37. Okay. The last bit, right? Before, or I suppose, second to the last bit before we end this discussion is now, what if we don't have z values? What if we haven't standardized? Well, it's very easy to standardize, right? If you remember from earlier, the z-score is just taken from the x-score minus mu all over your sigma. But of course, you can only standardize if you know the mean and the standard deviation or the variance, right? What if we're not dealing with z-scores, like we are dealing with x values? We can just, right, standardize. We have here a normally distributed variable x with a mean of 18 and with a standard deviation of 2.5. We want to get x is less than 15 and x is between 17 and 21. Well, we can turn this into z is less than 15 minus 18 over 2.5. 3 over 2.5, that is 1.2? Or negative 1.2? 15 minus 18 divided by 2.5. Yeah, negative 1.2. Okay, so this is just the same as z less than 1, negative 1.2. This is just going to be 17 minus 18 or 2.5. This is what? I don't know. Minus 0.4? Is that right? Yes, minus 0.4. And this one now is 21 over 18. 21 minus 18 over 2.5. This is 1.2. So this is the same thing as the probability that your z-score is between 0.4 and 1.2. For this, I'll just bust out my calculator so that we're done very easily, right? This is x is less than 15. X is less than 15. So in this case, if I were to draw this z-score right here, this is negative 1.2 right here, less than 1.2. So we just put in our calculators. P of negative 1.2. This should be good enough. Oops. Shift 1, 5. Oh. Shift 1, 5, 1. Negative 1.2. That gives us a value of 0.115070. Okay. Then from here, we just do P 1.2 minus P negative 0.4. Isn't that a breeze? Right? Isn't that a breeze? P 1.2 minus P negative 0.4. We will get a value of 0.540350. Isn't that so great? Very easy. Even without the use of, especially it's because without the use of tables. Okay, let's do another simple example. A research scientist reports that mice will live an average of 40 months, okay, when their diets are sharply restricted and then enriched with vitamins and proteins. Oh, really? Okay. Sorry, I'm just very curious. Life expectancy of mouse. Oh, okay, there you go. Right? Average of 40 months. So that is more than 3 years, I suppose. When their diets are sharply restricted and then enriched with vitamins and proteins, assuming that the lifetimes of such mice are normally distributed, and most usually it really is normally distributed, with a standard deviation of 6.3 months. Find a probability that a given mouse will live more than 32 months, or in this case, P of X is bigger than 32. Notice that the average is 40 months. So if we're going to think about this as as a what do you call this? As a normal distribution, 40 is here, which means 32 is here, and you are living more than 32 months. Oh, it's the same thing like this. Okay. But we don't have this standardized, so let us standardize. Z is more than, right? 32 minus 40 over 6.3. This has the same effect as 32 minus 40 divided by 6.3. This is now the same effect as P. Z is greater than negative 1.2698, 1.27. Right? The thing about this is that I am a little bit uncomfortable because technically the answer to this is negative 1.26984127, so on and so forth. And we just had to round off, which was rounding up in this case, right? But the thing in here is that what if I get an answer that is, I don't know, say for example, 1.265. It is halfway between 1.26 or negative 1.26 and negative 1.25. In that case, how would you do it with the z tables? Well, you just get the value of negative 1.26. Say, for example, negative 1.26, negative 1.20, 1, 2, 3, 4, 5, 6. So this is for 5, right? Negative 1.25, that gives you a probability of 0.1056. For negative 1.26, you get a value of 0.1038. What I would do, and of course what every engineer would do, it's in the middle of this, right? The negative 1.265 is in the middle. Therefore, we get the average. Get the average, which is 0.1047. There you go. That's how you, oops. My There's my pen. Okay. It is 0.1047. Okay. The thing with this is that, well, this only happens in very fringe cases where it's 1.265, right? If it's 4, then I could more comfortably write that down as negative 1.26. Okay. But in this case where it's half and half, you just average the two values. But in this case, you don't need to, well, round down or remove information. What you can just do is, of course, just write it down on your calculator. R, right, of 32 minus 40 all over 6.3. It will do its magic for you. Say, for example, of course, if 153, oops, 153 R of 32 minus 40 divided by 6.3, and what you will get is 0.89793. 0.89793. Okay. That is what you would do. And let's just see if this is indeed correct. For negative 1.27, negative 1.27, 0, 1, 2, 3, 4, 5, 6, 7, 1 point, sorry, 0.1020. 0.1020. Of course, we're now getting the area to the right. So 1 minus that value is going to be, I should really stop drawing somewhere here very close to my face. Sorry. That value is 0.897930. And this is a value of 0.897. Oh, sorry. 8978. Sorry, 8980, which is close enough, honestly. Right? So there you go. That's how you do these simple examples. Note that you are provided a lot of information in this case. Okay. There you go. There it is, 0.8980. But of course, you don't need to do this if you know how to, fiddle around with your calculator. Given a normally distributed variable x with a mean of 18 and a standard deviation of 2.5, oh, sorry, not that, 18 and the standard deviation of 2.5, we need x such that it will make this be 0.2236 and this be 0.1814. We have two different values of k in here. This one is easy enough because we just need to backtrack with the tables. 0.2236, this is x is less than that value. So this is what the tables really do mean, right? Something like this, something here, and this is the value of k that we need. But notice that in this case, we are drawing in here x values. What the table suggests are z values. So let's just go and get that first. 0.2236. There it is. That is going to be negative 0.7, 0, 1, 2, 3, 4, 5, 6, negative 0.76. Note that in this case, your z value is negative 0.76. You're going to have to backtrack because you need to find the x value, not the z value. X minus 18 all over 2.5. Of course, you can just solve this using your calculator. Negative 2.5 times 76 plus 18. You will have 16.1. K is equal to 16.1 over here. And in this case, we now have x is greater than k is 0.1814 somewhere here. This is your value of k. But again, this is for a z value. Sorry, this is for a z-score if you're looking in a table, right? So in this case, 1 minus 0.1814 gives you 0.8186. Okay, so we go now there. Actually, I can just do this here. 1814. There it is. 1814. This is now 0.91. 0.91. There you go. 0.91. And in this case, 0.91 is equal to x minus 18 over, 2.5. 0.91 times 2.5 plus 18. This gives us 20.275. Okay, K equals 20.275. That is how you write down, or now that is how you backtrack. Notice we're just combining here the backtracking mechanism based on our Z table and the standardization. Okay. And then I think, right? Oh, still a lot of other examples in here. We will have, oh, sorry. Let's stop there let's stop. I wanted to go forward just to know like how many other examples we have. We can solve this one pretty quickly. Human body temperatures for healthy individuals have approximately a normal distribution with a mean of 98.25 degrees Fahrenheit and a standard deviation of 0.75 degrees Fahrenheit. Notice that because this is small, you expect this to be very tall, very spiky, right? Excuse me. Now, find the 90th percentile of the distribution. What do you mean by 90th percentile of the distribution? If we remember back in, when was that? Topic 1, right? A quartile is basically you are now chopping this up into 4 equal parts. 4 equal parts wherein this is 0.25, this is 0.25, this is 0.25, this is 0.25. We are basically doing that, but for percentiles. Or in this case, you're going to chop everything up such that all of them have 1%, right? In their, how am I supposed to say this? In their, how am I supposed to say this? The areas pala. Sorry, that is a major brain fart right there. So what we want is basically to find this value in here such that this thing is 0.90. This whole area right here is 0.90. Right? Find the 90th percentile of this distribution. Note that in this case, what I'm talking about in here are currently Z values, right? Z values. So in this case, very easy for me to understand. Okay, I just need to find a value such that your Z is 90. So let me see in this case. Sorry, no, 90. I don't think so. Yeah. 90. Who's the closest to 90? Somewhere in here, somewhere in the middle in here, 1.28 something, right? And at that point, well, I'm not sure which one to place it in. So what I'm going to do is just take the middle. I know it's not the middle. I know it's not the middle. This one only has 0.003. Oh, sorry, 0.0003 before it gets to 0.9. This one has 15, 0.0015 before it goes to 0.9. But you know what? I'll take it, right? That is going to be, what is this again? 1.285, okay? 1.285. So my z-score in here is 1.285. And let's backtrack that. 1.285 is equal to x minus 98.25 all over 0.75. If we do this, we will get 99.21375. 99.21375 degrees Fahrenheit, of course, right? So something like, I don't know, 99.21 is good enough. I think maybe, right? Let's see what their answer is. There it is. The probability closest to 0.9. Oh, they want the closest, which is 1.28. So in this case, if they say it's 1.28, we will have 99.21, and there it is. Okay, that's your value. Okay, last bit before we go, right? Before we go, we have here, when can you approximate something as a normal distribution? If we remember from back when, right, from way back when, right, the hypergeometric can be approximated as a binomial when blah blah blah, right? When specific what do you call this? When specific things are supposed to happen, right? When, say for example, a binomial can be approximated as a Poisson distribution when blah 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 blah. In this case, the normal distribution can be used as an approximation to the binomial if, number one, the number of trials is large. I think the cap in here, or rather, you can start thinking about this as a normal distribution if n is like 100 ata yun. I think if n is bigger than 100, I'm pretty sure. Right? And when these values are both bigger than 5, note that in this case, the P in here is probability of success and Q is the probability of failure. Both of them have to be bigger than 5 for you to understand, right? That, well, this is a big enough kind of a normal distribution. Or sorry, this is a big enough kind of a data set or a sample set such that, well, it's normally distributed. Why? I don't know if the central limit theorem is part of FNDSTAT. So for now, I will leave you guys on a cliffhanger why that is. But in this case, yes, you can approximate it as a normal distribution. So in this case, the values of mu and of your mu and your sigma really are the values of mu and sigma that you are going to find in a binomial distribution. If you remember, in the binomial distribution, where is the binomial distribution? This one. The values in here are NP for the mean, and for the variance, it's N times P times 1 minus P, or Q. Oh, so in this case, your sigma really is square root of NPQ, which is here. Right? So that's what we want. Always adjust x before transforming it to z, since x is a discrete random variable whose probability is being calculated using a continuous probability distribution. This is very interesting because now, once n is large enough, once your NP is bigger than 5, once your NQ is bigger than 5, at that point, you can now think, oh, pwede nang gawing continuous. Very interesting. Right? Let's try this out. Statistics released by the National Highway Traffic Safety Administration and the National Safety Council show that on an average weekend night, 1 out of every 10 drivers on the road is drunk? Oh my goodness. 10%? So that means your Q is 0.9. If 400, oh my goodness, 400 drivers are randomly checked next Saturday night, what is the probability that the number of drunk drivers will be less than 32? So in this case, you will, you will tear your hair out because what you're going to have to calculate, right? This is very clearly a binomial distribution, right? But what you're going to calculate 400 choose 0, and then 0.1 raised to 0, 0.9 raised to 400, plus 400 choose 1, 0.1 raised to 1, 0.9 raised to 399, so on and so forth, up until you get to 400 choose 32, 0.1 raised to 32, 0.9 raised to 368. No one wants to do this. Instead, because you understand, wait a second, your P is 0.1, your Q is 0.9, your N is 400. That means that my NP is 400 times 0.1, which is 40. And then my NQ is 400 times 0.9, 360. Wait a second, both of them are bigger than 5. I can make this into a normal distribution. And what is the mean and standard deviation of my normal distribution? Of course, it will be NP, and your sigma will be square root of NPQ. In this case, NP is really just 40. And then in this case, your sigma is going to be, let me get this now. Wait a second. NPQ. NP is 40. And then Q is 0.9. This is 36. Oh, this is 6. Very nice. So that means now you have your mean is 40, your sigma is 6, right? Or your standard deviation is 6. Less than 32 will now look something like this. This is 40. The mean is 40. You're looking at 32. Less than 32 is this area right here, which, if you just plug it into your calculator, will be P of not 32, right? But 32 minus 40 all over 6. In this case, this will be P P of -8 over 6, -4 over 3. Well, -4 over 3 works. We will have 32 minus 40, -8 over 6. We will have 0.091211. 0.091211. So there's about a 9% chance that the number of drunk drivers will be less than 32. Very scary to think about, I suppose. Okay. That's it. I think, yep. There we go, 0.0918. Oh, because they use -1.33 lang. For us, I think we made it very clear that this is more exact, right? 1.3333, so on, right? For them, it is 0.0918. For us, it is 0.0912. Completely fine, of course, right? And, oh, there's more. Okay. The probability that a patient recovers from a delicate heart operation is 0.9. Good. Of the next 100 patients having this operation, with its probability that less than 30 survive, and between 84 and 95 inclusive survive. Okay. So let's turn this into P is 0.9. Your N is 100. That means that your NP is 90 and that your NQ is 10. And in this case, oh, both of them are bigger than 5. Therefore, we can turn this into a normal distribution, right? The normal distribution in this case has a mean of course, 90 and a standard distribution of 93. There you go. So this is just going to be N times P. So that's 90 times Q, which is 0.1, which is 9. Square root of 9 is 3. There you go. Less than 30 survive. In this case, we just need P is X is less than 30, or in this case, right, less than 30 ito, right? So this is going to be P of 30 minus 90 over 3. Right? Less than 30 survive. Is this real? This is very small. Wait, this is really very small. -60 over 3, -20. Okay, so suffice to say, this is not gonna happen, right? This is not gonna happen. B, -20. Apparently, my calculator says 2.9733 times 10 raised to -89. That is how unlikely it is. Of course, there's still a chance that only less than 30 people survive, but it is not very probable. Okay? Between 84 and 95 inclusive survive. So in this case, 84 and 95 inclusive. Okay? So in this case, we can turn this into, of course, Z scores 84 minus 90 over 3 Z, and then 95 minus 90 over 3. And then what you will have is basically 84 over 90. 84 minus 90, -6, -2. And this is now 95 over 90. That's 5 over 3. So 5/3. So basically, right, this is going to be P of 5/3 minus P of -2. This case, 5/3 minus -2. This is a very good chance, 0.92946. Okay. 92946. So there you go. That is the everything that you need to know, I suppose, about normal distributions for now. Right? We will complicate it next time. The complication is, what if you don't know what the mean and standard deviations are? How will we solve then? Right? So that is it for now. I will see you in the next one. Thank you very much.